Axioms, the foundation of any probability model. Non-negativity, 0 less than or equal to P of A for any event A. Normalization, P of S equals 1 where S is the entire sample space, the set of all possible outcomes. Additivity, if A and B are mutually exclusive, they cannot happen together, then P of a union B equals P of A plus P of B. These rules guarantee that probabilities behave like numbers we can add, subtract, and compare. Sample space, think of it as the menu of everything that could happen. Example, rolling a fair 6-sided die. The sample space is the set 1, 2, 3, 4, 5, 6. Each single number is an outcome. Any set of numbers, such as 2, 4, 6, is an event. Counting techniques, before we assign probabilities, we often need to know how many ways something can happen. Permutations, ordered selections. NPK equals n factorial divided by open parenthesis n minus k close parenthesis factorial. Imagine arranging 3 different products on a shelf that holds 5 spots. How many ordered arrangements? Use permutations because the order matters. Combinations, unordered selections. NCK equals n choose k equals n factorial divided by k factorial times open parenthesis n minus k close parenthesis factorial. Example, picking a team of 3 managers from 10 candidates. The order of selection is irrelevant, so we use combinations. Real-world analogy. If you are dealing cards to 4 players, the number of ways to choose which 5 cards go to the first player is a combination, because the order of the 5 cards does not matter, while the order in which the players receive their hands is a permutation. Discrete distributions, binomial and Poisson. Binomial distribution models the number of successes in a fixed number n of independent trials, each with the same success probability p. P of x equals k equals combination of n choose k times p to the k times open parentheses 1 minus p close parentheses to the n minus k, where k ranges from 0 to n. Steps to use. Step 1. Identify n total trials in p, probability of success per trial. Step 2. Plug k, desired number of successes, into the formula. Step 3. Compute the combination of n choose k, and then the powers of p and 1 minus p. Business example. A sales manager knows that each cold call converts with probability p equals 0.08. In a day she makes n equals 25 calls. What is the probability she closes exactly 2 deals? P of x equals 2 equals combination of 25 choose 2 times open parentheses 0.08 close parentheses squared times open parentheses 0.92 close parentheses to the 23. Poisson distribution is useful for counting how many rare events happen in a fixed interval, such as time, area, or distance, when events occur independently at a constant average rate lambda. P of x equals k equals e to the minus lambda times lambda to the k divided by k factorial, where k ranges from 0 to infinity. When to use, if n is large, p is small, and the product np, the expected number of successes, is moderate, the binomial can be approximated by a Poisson with lambda equals np. Business example, a call center receives on average lambda equals 4 service requests per hour. What is the chance of receiving exactly 6 requests in the next hour? P of x equals 6 equals e to the minus 4 times 4 to the 6 divided by 6 factorial. Both distributions turn qualitative business situations, how many customers will buy or how many breakdowns will occur, into concrete numbers that support forecasting and risk analysis. A continuous random variable can take any value in an interval. Probabilities are obtained from the area under a curve called the probability density function, PDF, denoted f of x. The total area under the PDF equals 1. Uniform distribution, every value between a and b is equally likely. F of x equals 1 divided by b minus a for a less than or equal to x less than or equal to b. Mean mu equals open parenthesis a plus b close parenthesis divided by 2. Variance sigma squared equals open parenthesis b minus a close parenthesis squared divided by 12. Example, a bus arrives uniformly at random between 0 and 10 minutes after you get to the stop. The waiting time x follows uniform 0-10. The chance you wait less than 3 minutes is open parenthesis 3 minus 0 close parenthesis divided by open parenthesis 10 minus 0 close parenthesis equals 0.30. Exponential distribution models the time between independent events occurring at a constant average rate lambda. F of x equals lambda e to the minus lambda x for x greater than or equal to 0. Mean mu equals 1 divided by lambda. Variance sigma squared equals 1 divided by lambda squared. Business example. The time in days until a machine fails has an average of 5 days, so lambda equals 1 divided by 5 equals 0.2. The probability the machine lasts more than 8 days is e to the minus 0.2 times 8 equals e to the minus 1.6 approximately 0.20. Normal distribution, the familiar bell-shaped curve defined by two parameters, mean mu center and standard deviation sigma spread. F of x equals 1 divided by sigma times square root of 2 pi times x of negative open parenthesis, x minus mu close parenthesis squared, divided by open parenthesis 2 sigma squared close parenthesis. Key properties. About 68% of observations lie within mu plus or minus sigma, 95% within mu plus or minus 2 sigma, and 99.7% within mu plus or minus 3 sigma. Business analogy. Daily sales of a product often cluster around a typical value, the mean, but vary due to promotions, weather, and so on. Modeling sales as normal mu sigma squared lets managers estimate the probability of unusually high or low revenue. Understanding these PDFS lets you translate real-world continuous measurements, waiting times, lifetimes, monetary amounts, into mathematical objects you can manipulate for risk assessment and decision-making. Standard normal distribution, z-scores, and table use. Standard normal z-distribution, a special case of the normal distribution with mean 0 and standard deviation 1. Denoted z is n of 0, 1. Z-score transformation, any normal variable x is n of mu, sigma squared can be ray-scaled to the standard normal. Z equals x minus mu over sigma. The z-score tells you how many standard deviations a particular observation is from the mean. Using the z-table, the table or a calculator provides p of z less than or equal to z, the cumulative probability up to z. Example, suppose average monthly revenue is mu equals $120,000 with sigma equals $20,000. What is the chance revenue exceeds $150,000? Compute z equals 150,000 minus 120,000 divided by 20,000 equals 1.5. From the z-table, p of z less than or equal to 1.5 approximately 0.9332. Therefore, p of x greater than 150,000 equals 1 minus 0.9332 equals 0.0668, about 6.7% chance. Two-tail probabilities. Often you need p of absolute z greater than z. Use the table for p of z greater than z and double it. Interpretation. A z-score of 2 means the observation is higher than about 97.5% of all observations. Only 2.5% lie further out on that side. Statement: take a random sample x sub 1, x sub 2, x sub n from any population with finite mean mu and finite variance sigma squared. As the sample size n grows, the distribution of the sample mean x bar equals 1 over n sum from I equals 1 to n of xi approaches a normal distribution. Square root of n times open parenthesis x bar minus mu close parenthesis divided by sigma converges in distribution to normal of 0, 1. The arrow denotes converges in distribution. Practical rule of thumb. In most business applications, n greater than or equal to 30 is enough for the central limit theorem to work well, even if the original data are skewed. Why it matters? The central limit theorem allows us to use normal-based methods such as confidence intervals and hypothesis tests for any underlying variable, as long as we work with sample means or totals. Example, daily sales of a specialty product are right skewed, with many low sale days and occasional big spikes. The sales amount each day has mean mu equal $8,000 and standard deviation sigma equal $4,000. A manager looks at the average sales over the past 40 days. By the central limit theorem, x bar is approximately normal with mean $8,000 and standard error sigma divided by square root of n equals 4,000 divided by square root of 40, which is approximately $632. To find the probability that the 40-day average exceeds $9,000, Compute z equals 9,000 minus 8,000 divided by 632, which is approximately 1.58. Using the z-table, the probability that x bar is greater than $9,000 equals 1 minus 0.9429, which is approximately 0.0571, about 5.7%. Key insight: even though individual daily sales are not normal, the average of many days behaves almost like a normal variable, making rigorous statistical analysis possible. Explanation: confidence intervals, CIS, using the normal approximation. A confidence interval gives a range of plausible values for an unknown population parameter. Mean mu or proportion p. The level, for example 95%, tells you how often such intervals would capture the true value if you repeated the sampling many times. 1. Confidence interval for a population mean. Known sigma, rare in practice. X bar plus or minus z sub alpha over 2 times sigma divided by the square root of n. Unknown sigma, typical case. Use the sample standard deviation S and the t-distribution with degrees of freedom equal to n-1. X bar plus or minus t sub alpha over 2, n-1, times S divided by the square root of n. Interpretation: a 95% confidence interval means that if we were to draw many samples and compute a confidence interval each time, about 95% of those intervals would contain the true mean. Business example: a retailer samples n equals 50 transactions and finds x bar equals $45 with S equals $12. For 95% confidence, t sub 0.02549 is approximately 2.01. The confidence interval is 45 plus or minus 2.01 times 12 divided by the square root of 50, approximately 45 plus or minus 3.4. So the manager is 95% confident. The average transaction value lies between $41.6 and $48.4. 2. Confidence interval for a population proportion. P hat plus or minus z sub alpha over 2 times the square root of p hat times 1 minus p hat divided by n. In a poll of n equals 400 customers, p hat equals 0.27 say they would recommend the service. 0.27 plus or minus 1.96 times the square root of 0.27 times 0.73 divided by 400, approximately 0.27 plus or minus 0.045. The interval 0.225 to 0.315 means the true recommendation rate is likely between 22.5% and 31.5%. These formulas turn sample data into actionable ranges that executives can use for budgeting, forecasting, and risk assessment. Hypothesis testing answers a yes or no question. Is there enough evidence in the data to support a particular claim? Step 1. State the null hypothesis H0, status quo, and the alternative hypothesis H. Step 2. Choose a significance level alpha, commonly 0.05. Step 3. Compute the test statistic Z or T. Step 4. Determine the critical values from the standard normal or t-table, or compute a p-value. Step 5. Decide. If the absolute value of the statistic is greater than the critical value or p is less than alpha, reject H0. Otherwise, do not reject. Section 2. Z-test for a mean sigma known. Z equals x bar minus mu naught divided by sigma over the square root of n. Use when the population standard deviation sigma is known, rare, or the sample size is large, n greater than or equal to 30, so S approximates sigma. Example: a company claims the average order value is mu naught equals $100. A sample of n equals 64 orders yields x bar equals $105 and S equals $20. Assuming sigma approximately 20, Z equals open bracket 105 minus 100 close bracket divided by open bracket 20 over square root of 64 close bracket equals 5 divided by 2.5 equals 2.0. With alpha equals 0.05, two-tailed critical Z sub 0.025 equals 1.96. Because 2.0 is greater than 1.96, we reject H0. The true average appears higher than $100. Section 3. T-test for a mean sigma unknown. T equals x bar minus mu naught divided by s over square root of n. Compare to the t distribution with degrees of freedom equal to n minus 1. Example, same data but n equals 15. T equals open bracket 105 minus 100 close bracket divided by open bracket 20 over square root of 15 close bracket approximately 5 divided by 5.16 equals approximately 0.97. Critical T sub 0.025, 14 approximately 2.14. Because 0.97 is less than 2.14, we do not reject H naught. Section 4, Z-test for a proportion. Z equals P hat minus P naught divided by the square root of P naught times 1 minus P naught over N. Example, in a market research sample of N equals 200, P hat equals 0.48 says they would switch to a new brand. Test null hypothesis P equals 0.55. Z equals open bracket 0.48 minus 0.55 close bracket divided by the square root of 0.55 times 0.45 over 200, approximately negative 0.07, divided by 0.035 equals negative 2.0. Critical Z sub 0.025 equals plus or minus 1.96. Z is below negative 1.96, so we reject H naught and conclude the true proportion is lower than 55%. These procedures give MBA students a systematic way to turn data into decisions, whether to launch a product, change pricing, or keep an existing strategy. Sample size determination. Before collecting data, you often need to decide how many observations are required to achieve a desired precision, margin of error, at a chosen confidence level. For estimating a means, desired margin of error E, for example, plus minus $2,000. Known or anticipated standard deviation sigma. N equals open parenthesis Z sub alpha over 2 times sigma, divided by E close parenthesis squared. Example, a financial analyst expects the monthly profit variance sigma equals $10,000. To estimate the mean profit within plus minus $2,000 at 95% confidence, where Z sub 0.025 equals 1.96. N equals open parenthesis 1.96 times 10,000 divided by 2,000 close parenthesis squared equals open parenthesis 9.8 close parenthesis squared approximately 96. So about 96 months of data are needed. For estimating a proportion, desired margin of error E, for example, plus minus 0.03. Anticipated proportion P if unknown. Use the worst case P equals 0.5 because P times open parenthesis 1 minus P close parenthesis is maximized at 0.25. N equals open parenthesis Z sub alpha over 2 squared times P times open parenthesis 1 minus P close parenthesis divided by E squared. Example, a product manager wants a 95% confidence interval for the proportion of customers who are satisfied within plus minus 3 percentage points, using the conservative P equals 0.5. N equals open parenthesis 1.96 squared times 0.5 times 0.5 close parenthesis divided by 0.03 squared approximately open parenthesis 3.8416 times 0.25 close parenthesis divided by 0.0009 approximately 0.9604 divided by 0.0009 approximately 1067. Thus, at least 1067 respondents are needed. Finite population correction, FPC, if the sample is a sizable fraction greater than 5% of a known finite population N, adjust. N adjusted equals N divided by open parenthesis 1 plus open parenthesis N minus 1 close parenthesis divided by N close parenthesis. This reduces required sample size because you are drawing a large chunk of the whole. By planning sample sizes ahead of time, MBA students ensure that their studies are cost-effective while still delivering statistically reliable insights. A. Deriving probabilities from the normal curve. Problem: daily revenue X follows a normal distribution with mean mu equals $80,000 and standard deviation sigma equals $5,000. What is the probability that a randomly chosen day's revenue is between $70,000 and $85,000? Convert the lower and upper bounds to z-scores. Z sub 1 equals 70,000 minus 80,000 divided by 5,000 equals minus 2.0. Z sub 2 equals 85,000 minus 80,000 divided by 5,000 equals 1.0. Look up the cumulative probabilities. Probability of z less than or equal to minus 2.0 is approximately 0.0228, and probability of z less than or equal to 1.0 is approximately 0.8413. The desired probability is the difference. Probability that 70,000 is less than or equal to x less than or equal to 85,000 equals 0.8413 minus 0.0228 equals 0.8185. So there is about an 81.9% chance the revenue falls in that interval. B. Applying the central limit theorem to non-normal date. Problem: the weekly demand for a niche product is highly right-skewed with mean mu equals 150 units and standard deviation sigma equals 60 units. A manager looks at the average demand over the next n equals 40 weeks. Approximate the probability that this 40-week average exceeds 170 units. By the central limit theorem, x bar is approximately normal with mean equal to 150, and standard error equals sigma divided by the square root of n, which is 60 divided by the square root of 40, approximately 9.49. Compute the z-score for 170. Z equals 170 minus 150 divided by 9.49, which is approximately 2.11. Using the z-table, probability that z is less than or equal to 2.11 is approximately 0.9826. Therefore, probability that x bar is greater than 170 equals 1 minus 0.9826 equals 0.0174, which is about 1.7%. C. Confidence interval and hypothesis test for a proportion. Problem: a survey of n equals 200 customers finds that p hat equals 0.4284 customers would purchase a new premium service. First, construct a 95% confidence interval for the true proportion p second. Test the manager's claim that at least 50% of customers would buy the service. Null hypothesis p equals 0.50 versus alternative hypothesis p less than 0.50 at alpha equals 0.05. Standard error equals the square root of p hat times 1 minus p hat divided by n, which is the square root of 0.42 times 0.58 divided by 200, approximately 0.0349. Critical value for 95% confidence is 1.96. Confidence interval equals 0.42 plus or minus 1.96 times 0.0349, which is approximately 0.42 plus or minus 0.0684. Resulting interval is from 0.3516 to 0.4884. We are 95% confident that the true purchase proportion lies between 35.2% and 48.8%. Test statistic z equals p hat minus p0 divided by the square root of p0 times 1 minus p0 divided by n, which is 0.42 minus 0.50, divided by the square root of 0.5 times 0.5 divided by 200 equals minus 0.08, divided by 0.0354, approximately minus 2.26. For a left-tailed test at significance level 5%, the critical value is minus 1.645. Because minus 2.26 is less than minus 1.645, we reject the null hypothesis. Conclusion: there is sufficient evidence at the 5% level to say that fewer than 50% of customers would purchase the